9. Yep.
Thank you.
Yep.
Yeah, looks like I'm the last one between you and lunch. We heard a lot about artificial intelligence yesterday and also today, and I want to show you one more aspect. And I'm not sure how many people have talked about semantic AI in this conference and about semantic technologies. Until we got this resolved, I'm just continue talking. We are a company that is specialized in retrieving information from the World Wide Web, the surface web, where Google is crawling around, and also from the deep web to help mostly pharmaceutical and bioscience companies to get access to resources that they cannot find when using the public search engines. That's how we started. That's how we were approached in the very beginning, about 3 years ago when we started this company. And what we call this now is managed intelligence. Managed intelligence because we provide information to certain areas in the company, very specific information that we discovered on the web, and that we provide directly to the people who are interested in this kind of information. Our technology is based on 3 pillars. This is, first of all, big data analysis technologies, like really being able to look into text, into numbers, and get information out of that. Of course, web technology, we need to be able to crawl information in the web. We can crawl the surface web like Google does, but we can also crawl the deep web. That is, whenever you have to enter data into a form, click search, you need to know what kind of data do you have to provide. Google cannot know that. There are approaches where these public search engines try to do that, but they randomly shoot information at these forms and submit them. And I do not think that this is a very good approach, because you really need to have some knowledge to be able to do this. So when we go to our customers, we usually come to a situation like this. These companies have, mostly out of the old libraries that were dealing with books before, they have a team of specialists, information scientists. They do expert searches for different parts in the company, be it competitive intelligence, regulatory affairs, research and development, a lot of more. So they have the knowledge to bridge the gap between the knowledge of these people here. They understand what they are looking for, and they know how to search either databases they have licensed, all kind of repositories, or now, and much more, the information that they find in the web. But what's happening is, since Google is getting almighty everywhere, and the other search engines as well, the companies start to reduce the size of these teams, saying the licensed databases are getting less and less. Google is becoming more powerful and more powerful from day to day. So they think, and we find this in the industry very, very frequently, that people start to believe, unconsciously probably, that what they cannot find in Google doesn't exist. We call this the public search paradoxon, because of course this is not true. I mean, we know that Google may be able to access only not even 20%, let's say, of the data that's in the internet. We know it cannot access all the data that's lying in these databases. But still people tend, I think it's laziness probably, I don't know what it is, but people really believe when they do a Google search and they don't find anything, that's what it is. And when we started, we had to prove these decision makers on the right side first that we are able to find information that they do not find in Google. And when we started, we said, we probably won't find data that Google does not have in its repository. But you won't find it because Google does not understand, when you enter these search terms, what you are after. That was pretty easy to prove, because when you then get the search results, when you do it in a manual different search, or when we found it, you can go to Google and you see, okay, the data is really there, but I just didn't know how to ask for it. But then something strange happened. I mean, our software, we deliver a development environment to the customer so they can build search engines using our software themselves. So we just did what we were asked to do, like the first thing we built was a crawler environment where we were going to the web, and we were crawling websites, and we were trying to find, this was the first one here, the search corpus, we call the search corpus with startup companies. And This was just like getting URLs of startups, crawl their websites, and put them in our search corpus. One-dimensional approach. But then these scientists started to do something completely different. They started crawling like the German library and were searching for the theses of people doing their PhD last year in medicine. Then they took out the names. You can do data extraction. Then they were crawling American websites, research projects on American websites. And they were getting the names of the people, the postdocs on these projects, matching them to the names from the German database, and putting the content of the research projects in the search corpus, basically tagged by the names of these people. And then they were able to enter the name of some protein or something and got the names of the people up that had experience with that. And they knew these people most likely speak German because they wrote their thesis in Germany. So that's how they find people who they are interested in. And they did this within 3 days. So when we noticed that's when we decided we want to have a company, because what we developed was really something special. Because Google definitely cannot do this. This is much more than you can do with a public search engine. So the next step then was to annotate the content using ontologies to make searching easier, to have faceted search, if it is by disease or if it is by location in the world, whatever you want to have to annotate your content with, and then cluster the content, put it in smaller bins, whatever, and then get this in user interfaces, in search interfaces where you have easy way to access it. Then the information scientists can use that to then publish the information to the decision makers. That is the old workflow, but now tool supported. This part here is completely automatic. This part here then is still manual. But what is now happening more and more is that we give these decision people that need the information, that they get direct access to the information in the systems here. So the power of these people is actually, which were kind of shrinking, because for me, this is like the libraries in the beginning were books, then they got these first databases, then they got the online databases, then they got the internet, and now they have to be able to manage the content in the internet, the intelligence that they find in the internet, and that's why we call this managing intelligence. So going back to that very first project that we did, that was the startup search corpus, we have right now about, this is not the correct number, about 40,000 companies. Now we have licensed Crunchbase. Crunchbase is a huge venture capital portal. They have about 700,000 companies listed there. Not much information about the companies. They are categorized, but these categories are, not good quality. It's going too fast. So seeing that this is not only pharmaceutical or bioscience companies, we assume that there are about 10% of these companies valuable for us. But how can we now find out which of these 10% are interesting for us? The idea is that we need classification to really find out what kind of company is this. First of all, understanding if this is a pharmaceutical company is not difficult. We just take the right concepts from our ontologies, see if these appear in the websites. But if I am searching, for example, for a company that has or is licensing a technology that allows me to do some gene manipulations, and I want to find such a company, and then a client research organization that provides me the services to do that with their technology, but is not licensing their technology, would be a false positive hit when I'm searching, would be distracting. So I need to somehow get these client research organizations out. And that's when we come to the point where we crawl the websites. Then we do an automatic classification using machine learning to get to the 10% that are interesting for us. The thing is that then we have about 100,000 websites, which means it's roughly about 5 terabytes of content. So you need to process 5 terabytes of content to be able to decide if this is now a CRO or some other website. The people in regulatory affairs or competitive intelligence or research development, they have different interests. So some might be interested in these CROs, some might not be. So this classification and then subdividing before actually annotating the content is very important to reduce the amount of content that we need to process. We chose a machine learning approach to do that. And the requirements here are pretty hard and not really suitable for anything that has to do with artificial intelligence. You might have heard, I'm not sure if anybody really talked about the massive amounts of data you need to train an artificial intelligence algorithm. We tried, in the very beginning, we tried neural networks, which is even worse than if you use classical machine learning. So we decided at the end to use classical machine learning because we have so small data sets. Then we also have to be able to change the data sets quickly because new requests are coming from the end users. And we have to classify based on company websites. We have a lot, even more with startups, we have a lot of companies who have only one page, maybe very long. But then you have other companies that have like thousands of pages on their website. Still, they might both be CROs. Then companies may fall into several classes. So it's not possible to use one classifier that just separates them into different classes. You may have to classify several times. And we have really training data sets, which is very hard, that are less than 50 samples per class. And if you look at ordinary or classical artificial intelligence or machine learning algorithms, we are not talking about 50 samples, we are maybe talking about 50,000 or 500,000 samples to get a training working. So the support vector machine, as we had it used in the beginning, would not work, like neural networks did not work. That's when we got to the point where we said, okay, let's try to artificially increase the training set. How could we do that? And we did that by using Thesaurus technology. Thesaurus is basically a kind of semantic network. So it falls into the semantic technologies part. And what we do is we get the vocabulary that is most importantly, and there we use already machine learning training mechanisms to get us the vocabulary that seems to be significant for a specific class. And then we develop, using our crawlers and using manual curation, we develop the thesaurus for that. And then if you look, for example, at the sample CRO website, you might have words like operation, propels, proof of concept, faster. And here you see like an entry in the thesaurus, fast and faster would match. So it would be changed to faster would be changed to fast. And all kind of terms that you think are similar would then be the same terms, which makes learning much, much, much easier. This led to the situation that we finally accepted, okay, this approach is working. We do not yet know how good it is working because we have to really test it with the real data. That means don't go away from the test data where we started with, let's go back to these 5 terabytes. And we integrated this in our environment. That's how our software looks like. So we built these classifiers here, and we had training data running. You can see here, in the beginning, we have in the 1, 2, 3, 4, the 5th column, the edited thesaurus. In the beginning, we were basically working without thesaurus. So we didn't do anything. We just used the dictionary. And we get a training accuracy of about 40%. Then we started to remove generic terms. You see below the table, there's a list of terms, what I'm referring to as generic terms, which actually increased or decreased the training accuracy. We did not do any research to find out why that was. But then we started to actually use terms from the ontologies that are used in bioscience and pharmacy, from MESH and some other terms from the client business, and curated that. And then we got to 75% training accuracy. And then we just played with the parameters a bit, and the final result is now at somewhere around 88%, which is pretty high. This is the point where we are right now. We still haven't managed to go through all the 700,000 companies that are listed on Crunchbase, because now we are in the process of solving the next problem. We cannot do this on the computers we are using right now. It's just too much data. So we are going to the cloud. That means we can distribute our software, the crawlers, through the cloud. We have to go into massive crawling and then also massive tagging of this content to be able to do this on a larger scale. But we have proven that the concept of combining classical artificial intelligence or machine learning approaches with semantic AI has a huge lever of improving the ability to apply these technologies. One other big benefit of following this approach in my eyes, and I'm reading more and more about this, is AI is a big black box if you do this purely numerical. I mean, we do not understand the mathematics behind neural network because the topology is too complex. But injecting semantic verification at certain points in the process allows us to verify in between if the results still make sense or if they are going in the wrong direction. And that's the path we are following, because we believe that in this, especially in this area, just doing black box AI or classification or recognition based on the crap data, and it's really crap data that you get on the web when you crawl these websites, is the only way that we can follow. And that's basically what I wanted to tell you. Thank you for listening.
Thank you. Does anybody have any burning questions?
You talk about the decline of databases and the loss of the expert being the librarian. I can see like the disintermediation of the librarian, but database sales and the STM industry is growing. So I don't see that. I don't like to understand where that assumption or belief came from. And the second thing is you talk about expanding and using facets with control vocabularies, thesauruses. How's that different from what discovery services do, whether the sort of the big ones like EBSCO or Summon, which have a lot of indexes and control vocabularies applied to content, or also things like Semantic Scholar and things like that? Is it because it's been applied to open web stuff, or is it?
Yeah, you gave the answer. It's applied to web stuff.
Okay, so that technology being applied in discovery services, just discovery services.
We can access this internal data, but in most cases we don't do that because there's actually a security issue. First of all, the contracts of the client, of our client, has to allow us to access the data in this proprietary databases. That is one thing. Then our services most of the time run in the internet and not in the corporate network. So when I'm talking about databases and repositories, I am more referring to data that is available within the corporations already, the silos, you know. And what we would like to do is combine information that we find in the internet with information we find in the silos, and get new insights into that by applying, of course, the taxonomies and ontologies. They exist. We don't create them. We just simplify them because we say for searching, the existing taxonomies and ontologies are too complicated. They are too vast, you know. And that part may actually be different because we really concentrate. We build a special search engine per perspective somebody has within a couple of hours or days, depending on how complex it is.
Thank you. All right, so.